Sound is on. Yes? Cool. Enter password. Okay. Are we there? Okay. Camera on the ground, watching the space shuttle or whatever crazy thing we're sending into space now by some billionaire in the world. Camera is mounted 3,000 feet from a rocket's launching pad, and the camera needs to pivot as the rocket is launched and needs to keep the rocket in focus. If the rocket is rising vertically at 800 feet every second, 800 feet per second, how fast is the camera to rocket distance changing when the rocket is 4,000 feet high? All right, so what do we got here? Let's see what's wrong here. There's our picture. And they said that the rocket is taking off at what again? We're going to call that H. The HDT is 800 feet per second. I need the labels. 800 positive, right? What else? That's all we know. That's about all we know, isn't it? 4,000. Oh, there's a sample in time, isn't there? So H is equal to 4,000 moment in time, right? 4,000 feet. So it's going to be 4,000 feet at one point. At that point, we want to know exactly how far it is from the camera to the rocket, which means we're using what? Seconds. Pretty obvious. No angles were mentioned. So it's x squared. I created my own monster, so I'll do x squared plus h squared is equal to C? There's a formula. All right, there we go. There we go. And I guess the camera's on the ground because I shot it all the way to the ground. Okay, anyway. So x squared plus h squared equals c squared. Are any of those constant? Yeah. Which one? Yeah. So 3,000 is constant. So I don't really want to take the derivative of x squared because it's going to be changed to 3,000 later anyway. So I'm going to change it now. 3,000 squared plus h squared is equal to c squared. All right, now we're going to take the derivative. Frankie, help me with the derivative. What is the derivative of this? Yeah. Perfect. Love it. And I can divide both sides by 2. Very cool with that. That's gone. That's a pretty easy problem, isn't it? What was h? 1,000. That was given. What did they say dH/dt was that? The 800? And C, can we find C with a little bit of simple math here? Tell me what C is, guys. I'll wait for 3,000. That's going to be 4,000. This is 4,000, wasn't it? Oh, isn't it a 3, 4, 5 right triangle? Okay. 3,000, 4,000. What would be the hypotenuse? 5,000. And we're looking for dCdt. Harper, what do you think that is? What is dCdt? Get some space here. Yeah, it is. But we'll get to get rid of 3 of them. So it'd be 32 and 5 zeros. Take away 3 of those zeros. So it's 32 and 2 zeros divided by 5. Am I okay with that? No one tells me if I'm right or wrong. I just make up stuff left and right. You guys cool with that? And I probably can count the nickels in $32, but I'd rather just have you tell me. How many nickels are there in $32? Oh my gosh, I should have just gone for it. I was going to say 640. Okay, so 640. I've gotten really good at basic money math. 640, and that would be what? Wasn't it feet? Feet per second. So that's how quickly that's changing. So how did you answer this question? Jonah, how would you answer this question? They asked, how fast is the camera to rocket distance changing? Cool now? Write down what you need to write down, guys, because we will have to do that when you do your answers. But right now, I don't want you to watch me writing a bunch of words you don't need to. Okay? Give me a second to get that. Get to the next one. There's a bunch here, guys. Still have 1, 2, 3, 4, 5 more. Yeah. then we'll be able to talk about every kind of related rate problem out there. All right, Evie, hope this is making sense for anybody watching. We use all throughout the years. I don't know if I can keep it for next year. We'll see. Everybody ready for B? What's going on B? Maddie, what are they asking for in B? Angle of, okay, so think about this, guys. If you use your arm as an angle of elevation, and I'm trying to watch something up in the air, I go like this, right? So the change in my arm from horizontal to looking at the object is this angle of elevation. Pretty cool? Let's draw that real quick. I'm thinking we're looking at this guy. Now, a lot of people like to use Greek symbols, so use theta. So that's going to be the angle. Awesome. Again, we know the same thing as what? 4,000 again? I couldn't do it there. I'm going to do it over here. So it's going to be height is 4,000. And again, that is a snapshot, one moment in time. It'll be 4,000. But we want to know if the angle is. All right. What's the formula? I think Pythagorean theorem is a waste of your time right now. Because we want angles. Pythagorean theorem doesn't give us angles. What? It is a trig ratio. It is inverse tangent. Very nice. I just go with tangent to start with. So tangent of theta would be what over what? Just literally in the picture. We can do that way, but then we still have to go find sine and cosine. What is tangent of theta? What ratio to what side to what side? Can we just call this H? Cool. What is opposite? Perfect. What is adjacent? Yeah, which is constant, so we can use it, right? Pretty cool. So now, kind of interesting. We've got everything we need, right? We just have to find the derivative of that. We want to change that tangent of theta. And we want to eventually see d theta dt. I don't really care about tangent change, but we can change that by, you were mentioning inverse tangent. That'd be a great plan. So I'm going to take the derivative, d dt. So Cooper, what's my derivative of the left side? Oh, and it's covered up. Sorry. The AD class, they did this pop quiz this week, so I covered them up. What do you got? Who remembers derivative of tangent? Secant squared. So we have secant squared. Good thing to memorize, especially when they're covered up. Secant squared theta times. Yeah. Remember, inside the tangent was theta. So now you do the chain. D theta dt. Very good. Because we don't know the change in the angle, and that's what we're looking for, right? We actually need that. That's actually what we're solving. So secant squared theta d theta dt. Cool. What's on the right side? I'm going to go over 1 over 3,000 for sure. Times dh dt. Because it's just like a 5h, it's a 1 over 3,000h. That's right. Cool? All right, so usually this used to blow me away. So I'm like, well, how do I go find theta? I have to go solve for theta? Not really. Let's just kind of see what we can do with this thing. Let's fill in what we know and see what we're looking for. All right, what do I didn't leave a lot of space here. Okay, so it's going to be secant squared theta. What should we do for secant squared theta? Well, you know what? Let's just actually try to find secant squared of theta. Would that help us? Let's try that. We said tangent of theta was h over 3,000. So what would secant of theta be? Secant is what over what? See, secant is 1 over cosine, right? And cosine is adjacent over hypotenuse. So this is what over what? I thought I made it obvious. Cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. Will that help us? We've got adjacent. We have hypotenuse. we could, I'm trying to think, did I go a route I didn't want to go? Let me think here. So, oh, don't we have a moment in time? It's going to be 4,000, so we can use that now. So what hypotenuse if the height was 4,000? Yeah, remember that? So 5,000, there we go. And that's 4,000, there we go. And that's our moment in time. So now, what is secant of theta? You said secant was 1 over cosine. Cosine is adjacent over hypotenuse. So this is what over what? Hypotenuse over adjacent. Cool. Hypotenuse over adjacent 3,000. We can make that nicer. What would that really be? 5/3. And square it. See what I want with that? So much easier. So then that's just going to be 25 ninths. Is that cool? So 25 ninths. I should have done this, not squared. So 25 ninths. Okay, now let's go back in. Because remember, I can do anything I want after we took the derivative. We're now at secant squared theta d theta dt. That ship has sailed. We're literally measuring the changes now. So I can use that sample point. So what am I going to have here? Secant squared theta was just what? 25 ninths times d theta dt, which we're trying to find. And what's on the right? 1 over 3,000 times d theta dt, I'm sorry, dh dt, which was what again? Is that 800 from before? Is that where we are? Okay, so still 800. All right, help me clean this mess up. What do we got? We are looking at d theta dt is going to be, well, I can dump 2 of the zeros. So it'd be 8 over 30 times the reciprocal, which is 9 over 25. I see some things happening here. What do you see? I can take out a 3. So that's now down to 10. That's down to 3. Is that it? Yeah, what's our final answer? Oh, no, I missed something. Oh, 8 and 10. Duh. Missed the easy stuff. 4 and 5. Final answer. Sorry, I don't do basic math like this. What do you got? Seriously.
Sorry, I got.
No, not just you. There's 6 others that could have answered that. What? I don't even need that. Just numbers. 12 over 20 over 25. Awesome. 12 over 125. Let's clean that up a little bit. 12 over 125. And that was, now be careful, what was that measured in? Oh, do we use degrees in calculus? Only what? Radians. That'll be radians per, I'm guessing it was second. Awesome. 12 over 125 radians per second. So, in that one, Kyle, what would I answer this with? What were they asking? I forgot. At pretty cool now. That's my related rate. That's probably about the ugliest related rate you can do when it comes to strange measures we're not always used to, but not bad. If you take the time to realize we can use those values on the triangle because we already took the derivative, we're in great shape. Okay? Pile of sand, very famous problem. There's a lot of these on the AP exam in the past talking about piling up rock onto a big pile, and they'll talk about removing the rock on the bottom of the pile while the crane brings in rock from the top, or they empty it on the bottom, and you get the difference in the two. This is just one measure, that's all it is. Sand is poured on a beach, creating a cone whose radius is always equal to twice its height. You'll see why that's important in a minute. If the sand is poured at the rate of 20 cubic inches per second, how fast is the height of the conical pile changing at the time the height is 2 inches? Okay, so we got to draw a cone. They have one there. We can kind of steal theirs. I'll just steal theirs. They cut off the edges. I don't know why. There's my cone. Cool. They know we're doing volume, right? Putting sand in a big pile, that'd be volume. They know the volume of a cone. It's just like a cylinder, but throw in 1/3. 1/3 pi r squared h. Pretty cool. So now here's the issue. if you deal with R and H, then you have to be looking for only one of them, but you have two. So what did they tell us about the relationship between R and H? Yeah, radius is 2 times the height. Now, here's where you have to look at the big picture. What are you trying to solve for? Which changed, the radius or the height? Height. So we are looking for, and this makes such a difference, and the next problem we'll really see it, dHdt. We're looking for dHdt. So will drdt be part of this problem? I hope not, because I don't know what it is and I don't know how to find it, right? That's why they tell us the relationship between R and H, so you can get rid of all the R's and deal with only H's. So what did you just tell me? You told me that R is equal to 2H. Cool. So let's go back to the volume equation. How could I change that equation to be nothing but H's? Well, I've got 1/3 pi. What's R? Ah, and 2H squared. Pretty cool. Easy. And then H. So I probably don't want to deal with a product rule if I don't have to. So what could I do to change that? Wouldn't that be 4/3? Is that asking too much? Is that okay? 4/3 pi times what? Nice. Like cooler? We just created a whole new problem with nothing but H's. Pretty cool. Now it's a pretty easy problem. You don't say that very often in a Calc BC class. It's a pretty easy problem. So I'm going to take the derivative of that with respect to time. Okay, Jackson, what's the derivative of that guy? You can just use the new found answer here. So the dv dt, I'll get you started, is equal to what? Uh-huh. Yeah, look how easy that is. Oh my gosh. And what do we know? We already know the height. Do we know the height? Height is 2 inches? Really? It's not very, oh, it's only sand. I thought we were talking about like rock or something, just sand. Somebody playing on the beach or something. 4 pi times 2 squared. Is that cool? And dH dt was what again? Oh, we don't. No, I'm sorry. That's the sand. That's dV dt, isn't it? We're looking for dH dt. My bad. Yeah, so much nicer. I wasn't paying attention. That's why you read them more carefully. So 20, or underline them to remind yourself. Okay, so I'm looking at it. It's going to be something divided by pi. And we're not playing the calculator game today, so you don't have to divide by pi. Just leave pi in terms of pi. So what is dH dt? So 20. What was it, divided by 20? Wouldn't 20 be already there? So 20 divided by, what do you think? Uh-huh. Uh-huh. And you want to solve for dH dt. So I want to divide by the coefficient of dH dt. That's all right. So what we got? You said 16. I like that, 16 pi. I can cut those by 4. Call that what? 5 over 4 pi? Don't get fooled and put pi in the middle. It's literally on the bottom. It's weird. You hardly ever divide by pi, but we're not going to change it. That's that. So my final answer, Maddie, would be what? I'll get you started. The cone. The rest of your cool. The cone. What about it? The cone's. Oh, what were they asking for? How fast is the? There you go. The cone's height is when the volume is. I shouldn't say that. When the height is. Sorry. What was our height? Yeah, I'm thinking that. Since they gave us that information, I don't know if they'd take off for it, but I would definitely say the height of this cone is increasing at a rate of 5 over 4 pi. What are we doing? Inches per second. Very cool with that? Good on that? Questions? Okay. That's our cone problem. Good stuff. Oh, there's no T, but there was an H. So I might say, and again, I wouldn't worry about it because I very rarely see a problem like this where they make you write out what it means. But I just want you to think about what it means. if you wrote anything, I'd probably write when the height is 2 inches, because there's a moment in time when the height is, I don't know when it was, but it happened somewhere. Kind of like IGT, we don't know when it happened, we just know it did. All right, so. And we're recording. All right, and we're back. Last problems, we're going to talk about the draining cone, draining tank of water, which is in a cone. And then we'll talk about me and my shadow, so shadow problem. So water is draining from a conical tank with vortex down. I guess it'd be kind of weird the other way. At the rate of 2 meters cubed per second. The tank is 16 meters high and its top radius is 4 meters. How fast is the water level falling when the water level is 12 meters high? So this one's real. We finally got something a little more real. Well, the sand was normal. That was real. Here we go. Here's our tank. I would like to do my little visual. It's leaking. There's the water coming out of the bottom. And what do we know about this thing? We know that it is draining, so that'd be dV/dt at -2, right? Because I know it's negative. Losing water at a rate of 2 cubic meters per second. The tank is 16 meters high, so I'll give it some dimensions here. So let me. And the radius is 4. Okay, how fast is the water level falling when the water level is 12? So we'll call that about right here. It's about 12 meters. So you can see the new problem. Those who have seen it before, you may still need a review as well. I don't know if I remember this stuff unless I get a nice review on it. Does everyone see the equation? Neither do I. Do you? You remember it, Harper? It's tough. It's not the equation you're expecting. Let's go through the ones we know. Is it an area problem? Not an area problem. Is it a Pythagorean theorem? No, not going to do any good. I see two different size shapes. What do you think, Jackson? It's not something you expect, but maybe you're seeing it. I'll give you the clue. Here's your clue. There are two different triangles. Different triangles. Related as well. I see it? Kind of. I like that idea. They're definitely related. Let me go ahead. Let's take a snapshot, or let's take a cross section of this. We're going to cut right through the middle. Now, not only is it leaking, we're going to cut it down the middle. And we said this was what, 4? This was 16. Then I'll go blue. This is going to be what, 12. And this is going to be R. Everyone see the two triangles? Are the triangles congruent? Give me a yes or a no. Are the triangles congruent? Does everyone see the two triangles? There's the big one, which goes 16 high, and the shorter one, which goes 12. Let me ask you again, are those triangles congruent? I said one is 16 high, one is 12. Are they congruent? No, they're not congruent, but what are they? They are similar. Everybody see it? One inside the other. Now, if you remember, I used to love teaching this part in geometry, and all my students struggled so much with it. That's why I love it so much, because I can help people see this. Give me a ratio that makes sense. What to what? Anything that makes sense, I'll take it. 12 to what? Where? 12 to what? I don't have a 30 or a 3. 12 to what? 12 to 4. I like that. So you did, I don't know if I like 12 to 4. You're saying 12 is the height of the small triangle to the base of the big triangle? That didn't make any sense. I want something logical. 12 to what? 12 to R. So height of the small triangle is to radius of small. See the logic we've set up? There's other ways to do it. That's one way. So 12 to R. Now that we've established that pattern, what's next? 12 is to R as 16 is to 4. Everybody see it? 16 is to 4. Here's the coolest part. We're done. When you cross multiply, you'll have an equation. We'll take its derivative. We'll be done. This is one of the easiest yet most difficult problems out there. Because everybody goes, I don't even know where to start. What's the relationship? It's not Pythagorean theorem. I don't know what I'm doing. But if you take that and go, oh, wait a minute, you had the change in the triangle because the height is changing and the radius is changing. So that's all related. The cone's not changing size. It's the same cone. So it's a similar triangle. So we give you cross multiply. 16r is equal to, oh, I messed up. I'm sorry. Which one of those can I not put in there yet? Remember, it's only when it happens. 12. 12's got to be replaced with h. We okay with that? Silence worries me. We okay? Okay, so 12 is really h. My bad. I got ahead of myself, getting all excited about it. So it's really 16r equals what? 4h? Now it looks like a little more of an equation, right? So if I take the derivative now, because I don't have to do anything else, that's the relationship. It's just a similar triangle. So what would that be? Frankie, what's the derivative now? That's it. Again, one of the easiest and yet most difficult problems out there. What do we know? Oh, what did I mess up? What did I mess up? They gave us dv dt, didn't they? I worked too hard. I was thinking of a different problem. Sorry about that. Pause. Not the whole thing. Don't blow it up completely. Just do this. Okay. Pay no attention to the stuff here. Little Wizard of Oz here. Pay no attention to the guy behind the curtain. Big mistake. Glad nobody's watching this video. Oh, sorry, Evie. Okay, so here we go. So we have that. Let's go back to it. Cross multiply, what do we get? 4h is equal to 16r. Why was I wrong? It's a great way to learn from this. Why was I wrong? Why couldn't we go on? Yeah, I don't have drdt. I was given dv dt, and there wasn't even a v in this problem, right? That's a problem. All right, so let's go back to what is the volume of a cone? 1/3. I should know by now. R squared h. Cool. So now, what are we looking for? I don't know why I convinced myself. I was already thinking of a shadow problem. No, I just gave that away. Okay, so what do we do here? Do we like a v, an r, and an h in the same problem? Do I really want to do product rule here? No, because I don't even have it. Didn't you just tell me you don't even have the RDT, right? I don't know what that is. How quickly is the radius changing? Don't know. So what do we have here? What are we looking for? How fast is the... we're looking for dHdt, right? So back to our plan. Let's rewrite this thing in terms of nothing but h. How are we going to do that? This is all you know. Tell me what to do. Cool. R is equal to, is it? 1/4 h, yeah. 1/4 h. Okay, so I'm going to replace the r with a 1/4 h, or h over 4. So it'll be 1/3 pi times h over 4 squared times h. Please clean that up for me. What do we got here? I'm going to go with, I'll take the bottom. Is it 48 on the bottom? I'm just too good for my own abilities sometimes. All right, so pi on top, pi over 48 times h cubed. Cool. So there's my equation. Now we're ready for a derivative that actually lead to something. Okay, so d dt of the final form of this, which is just over here, would be dv dt. Oh, we'll get that in a minute. Yep. So dv dt is equal to, what's my derivative on the right? Pi. I'll take that part. I like it. 3 over 48, so 16. Pi 16ths, h squared, dh dt. Okay, so what do we know? You said dv dt was just -2? Okay, cool. And we had h as well, didn't we? H is 12. We can finally use it. So h is 12. So I've got negative 2 is equal to pi 16 times 12 squared dh dt. All right, the only thing that beat us up now is the algebra. It's negative 2 over 1 times, I'm going to just do reciprocal, that'd be easier, wouldn't it? It lets me block that in. Cool. Here we go. So dh dt is equal to negative 2 times, I believe it's what, 16 over 144 pi. Am I good? Okay. And if I'm going to clean that up just a little bit, I can cut this in half. Call that 1. Call this 72. 16 and 72, 8 can go in those, right? So 2 and 9. Negative 2 over 9 pi. Oh, why did I do pi on top? 2 over 9 pi. I just don't want to waste your time watching me do a bunch of calculations here. Negative 2 over 9 pi. Make sure I see the pi is in the denominator. And that would be final answer. All right, Jonah, you got this one? So it's negative 2 over 9 pi. What were we looking for? Cool. So the water level of the cone is? Nice. Per, what was it? I'm guessing seconds. Yeah, per second. Pretty cool. Now, sorry about the confusion in the beginning. It actually worked out kind of nice. Practicing moment, we can go back and check. So that's one where you need to change one of the variables over. In a minute, you're going to see the one I was getting it mixed up with is the shadow problem. And the shadow problem, if you think of somebody standing there and the light's behind them and the shadow is shining in front of them, creates a big right triangle, right? That's easy. But then if you think about the shadow from the pole and the person, that's two triangles, one inside the other, right? Because the top of your head is the lights. You're in the middle of the hypotenuse. So we're going to look at this real quick. Here we go. There you go. So everyone see the two right triangles now. If you don't see them, I'll put a little funny box at his feet and a box at the flag, at the post. Okay, so we have two right triangles. Let's get this one going. This one takes a little more thinking sometimes as far as what to label everything. So what do we want to label? Let's get a ratio going first. What to what? Is 10 one of the measurements of the triangle? We'll use a 10, but how are we going to use it? Well, I like that. So x plus 10 is to what? Is to x. Okay, if you want to do base to base, I'm with you. I will do that. See what he did there, guys? He did base of the big triangle to base of the small triangle. Now I want to do something with the big triangle, different dimension. 10 is to. Nice. Okay, cool. Now, when we cross multiply, all we're trying to find is what? Dx dt, I'm guessing, or something? What are they looking for? They're looking at what rate is the length of the shadow changing? Oh, so that's not x. That's actually, we have to call that. What would we call that? I'm going to call this little piece here A, and I'm only doing it here because isn't it only 10 for one moment, right? He didn't stay there. He's going to be moving, right? As he moves away, his shadow's changing, right? And he's moving away from the pole. Let's make sure we got that clear. How quickly is he moving? He's 10 feet away from a 10-foot tall lamppost, and he's moving away at a rate of 3 feet per second. So he will not be 10 feet for except 1 second. He'll be there for a second, then he goes to 11 and 12 and 13 and so on, right? So we're trying to see how quickly his shadow is changing, all right? So we're going to call that A for now. So they were kind of misleading. We probably should have done the box, right? That is a moment in time. There we go. So what can I call that? 10 really can't be used. Let's call that what? X plus A. Is that okay? Silence on that one. Very confused. Is that okay? X plus A. Because A represents any length that B is away from the pole. Okay? All right? So what are we going to get when we cross multiply? Let's try that. What's that going to give you? Well, don't hear it then. I'm just going to do it myself. 6x plus 6a. Yes? Agreed? Is equal to 10x. Please make it cleaner. What else can I do? Yeah, I like that. 4x is equal to 6a. Nice. So now you see how we're okay if we take the derivative, because there's no other dimension to worry about. There's no other variable that we have to bring into the story. We're going to take the derivative of this function with respect to time, and we're moving the person away from the pole at the rate they told us, and we'll see how quickly a is changing, right? So that's going to be, yeah. Not at all. Not at all. But I always feel like the easier, the more it's simplified, the less work I have to do with the derivative. So it's going to be what? 4 dx dt, yeah? Is equal to 6 dA dt. All right. So what was dA dt? Was that given? Yeah, isn't that how quickly he's moving away from the pole? So dA dt, A is 10 feet at some time, and it's 11, and it's 12, and so on. So the change in A over time is dA dt. You okay with that? So it's going to be times dA dt. And dA dt we said was what? 3? All right. Yes, it would. If he's going towards the pole, it'd be negative because you're decreasing the distance, and it's going away, so it's positive. So dx dt is all we're looking for, right? And that's going to be 6 times 3. Did I do that right? Yep. So I'm guessing dx dt is a pretty easy 18 divided by 4, what, 9 over 2? And that would be what? As the person's walking away from the pole, their shadow is what? Increasing at a rate of 9 halves, 4.5, whatever you want to do, feet per second. You okay with that? Not too bad. This one gets a little hard when you're like, well, which one am I talking about? So if I'm looking at the ADT, that's how quickly he is moving away from the pole. The XDT is how quickly his shadow, because remember, when you stand there and you watch your shadow get longer, it's comparison to you, not the pole behind you. It's comparison to where you are. So the change that the XDT is between his feet and the end of the shadow is changing at 4.5 feet every second. It's just going to get bigger and bigger and bigger. Will it ever get smaller? It would have to eventually. I guess you couldn't see it after a while. Maybe that's the case. Okay? So the last one is always the one that makes it seem so difficult, but it's actually one of the easiest ones. At what rate is the tip of the shadow changing? The tip of the shadow, what's that? Not the angle, no. The tip of the shadow would be dx dt plus dA dt. Does that make sense? Because if you want to know how quickly the shadows change, aren't they working together? One is increasing as you go away from the pole, and one is the distance between him and the end of the shadow. So the shadow itself is the distance from, we could do this, how about this? Me and my shadow. Do you even know that song? Probably not. So S is the entire shadow, right, which is from the pole creating the light, causing the shadow, all the way to the end. Wasn't that just A plus X? And wasn't the change in A dA dt? And the change in X was dx dt? So people, yes, it is that easy. The easiest thing we'll ever do in calculus is ds dt is dA dt plus dx dt. What did we say dA dt was? 3. And dx dt was? 9 over 2. So I'm going to go with 6 over 2, 15 over 2. There we go. They work together, right? Because one's increasing, the other one's increasing, and they're not overlapping. They're one leading to the other. So it's 15 over 2. I could say the tip of the shadow, since I only have to do one last one, I'll do it here. The tip of the shadow is increasing at a rate of 15 halves feet per second. Cool. All right, so we still have about 9 to 10 minutes left. So I knew that was going to take a while. I didn't know it would take that long, but it did. So check this out. Work on the worksheet the rest of the time. It is due on Wednesday. Okay, it's not huge. I know homework's not worth that much, but you want to be ready for the quiz on Wednesday, which will be you know how to do those problems. All right, let me shut this down and I'll answer your question.